Welcome, welcome, welcome to week 3 of the webinars that we're doing from A Plus College Ready. This one's about Unit 2, so we're going to take a look back at Unit 1, all about periodic trends and bonding, and then we're going to talk about how does electronegativity and stuff like that affect the bonding that we talk about in Unit 2. So, Unit 1, periodic trends, Unit 2, bonding. So just as a reminder, what are those periodic trends? Well, you've got radius, how big something is, and that could be an ion or an atom. You've got ionization energy, the amount of energy it takes to knock loose an electron. Electronegativity, when two things are sharing an electron, how strongly is one of those atoms pulling on those shared electrons? And then electron affinity is basically the opposite of ionization energy. As you add electrons to things, instead of removing them, as you add electrons, it releases energy. So ionization energy and electron affinity are very closely linked. For the periodic trends, you oftentimes see things like this with arrows that say, this is the way this trend goes, and this is the way this trend goes. And at the end of the day, this is true. Electronegativity does go over to the right and up, and atomic radius does go down and to the left. But remember that we have to think a little bit more about what we're doing and why it is what it is. So we're going to talk about not just what these arrows are, but why they are what they are. So this is from last week. Just to remember that when you answer questions that require you to justify a trend, you have to talk about both things, so not just one atom. You have to state the explanation they're looking for. So you can't just say to the right and up. You have to explain what you're talking about. You're going to try to refer to Coulomb's law as much as possible and emphasize that energy of attractions of protons and electrons, and maybe repulsions. Maybe you're doing that. So protons and protons. Coulomb's law is just this one more time for review. Q1 is the charge of one thing. Q2 is the charge of the other. So you could have 7 protons and 7 electrons. And then r squared down there, that's the distance between those things. So the distance from the nucleus out to where the electrons go. If we wanted to talk about electronegativity real quick, we'd want to pick 2 elements that we were reasonably sure we could compare. Now you wouldn't want to pick 2 metals here in the middle, because notice that the trend goes 154, 163, 166, and then back down. And so there's no clear trend here in the middle. So AP will always give you things that are pretty well founded and give you the ability to discuss what you know without getting to some of the, that doesn't make sense. So we're going to pick nitrogen up here at 3.04 and antimony. Those are 2 things that are in the same column, but on different rows. So we looked up the numbers from nitrogen and antimony, and we're asked to explain the difference. Normally, they would ask you to make a claim, but this time the claim is given to you. It's that nitrogen has a greater electronegativity. What's the data you have to prove your prediction? The data, if you remember, is the electron configuration and also the number of protons. So we can look up here and see nitrogen is going to be 1s2, so those first 2, 2s2, and then 2p3. So that's where we'll get nitrogen. And antimony is way down here and has 51 electrons. So we'll have to go 1s2, 2s2, and so on. And we'll get to the following data set. The data to prove our prediction is, here's the electron configuration of nitrogen. Here's the one for antimony. You could also include the number of protons. So its atomic number, or Z number, can sometimes be included. But we always consider, are they on different rows? Are those electrons in different energy levels that we're talking about first? We only really need to worry about protons when we go, oh, look, they have the same number of layers of electrons. So then we would explain how the data supports our prediction. So according to Coulomb's law, the farther away from the nucleus, the less force of attraction on the electrons. Since antimony has 5 energy levels and nitrogen only has 2, there's less pull on the electrons from antimony than nitrogen, and thus antimony has a lower electronegativity. Now, notice that this is not really an incredibly right answer. So on Pear Deck, I would invite you to draw anywhere on this slide and kind of mark out, what do you think the wrong parts of my answer are? All right, now that you've drawn them there and I've looked at your answers, let's see what we could cross out that seems kind of wrong. Aha. Saying that antimony has 5 energy levels and nitrogen has 2 is kind of correct, but not quite. So how many energy levels does antimony, Sb, have? It has all of them, all of the energy levels. It may not have electrons in all those energy levels though. So just saying has 5 energy levels is not really true, because that's not what we're trying to say. We're trying to say that its valence electrons are in the 5th energy level. And nitrogen doesn't have just 2 energy levels, it has all of the energy levels. So we have to be able to say, wait. How can I back up and say that that's where the electrons are? Is there a better way to word this? And then there's less pull on electrons from antimony than nitrogen. I don't really know what that means. I mean, antimony has more protons, so antimony would pull harder on the 1s electrons than the 1s electrons from nitrogen would. So antimony will pull harder on those 1s electrons than nitrogen would pull on its 1s electrons, because it has more protons. So this answer isn't quite right. So let's see how we can clean this up. And I've changed it to, since antimony has 5 occupied energy levels, that's a better way to say that. And nitrogen has 2 occupied energy levels. And then the only other change I've made is to say there's less pull on valence electrons. And electronegativity ends up being very, very important, because it's electronegativity that we use to figure out what kind of bond are we going to have. Remember, the other tool that we talked about last week was PES, or using light to try and knock off electrons from an atom. So remember these peaks, the height of the peak told you how many electrons, and where it is here on the x-axis tells you something about how much energy it takes to remove those electrons. So here are the 1s electrons, and they're very, very close to the nucleus. Whereas the 2s electrons, they're farther away from the nucleus, and so they use less energy to remove them. So we have lots and lots of different types of bonds, right? Now, there's hydrogen bonds and some other ones that you may remember from chemistry, but we're not talking about those. London dispersion forces and stuff like that, that comes later. For right now, we're just worried about intramolecular, meaning inside of a molecule. So we've got ionic things, right? And we've got covalent things, and we've got metallic things. So which one is made of metals and nonmetals? So students on Pear Deck, you can go ahead and drag the icon to either ionic, covalent, or metallic. Which one is metals and nonmetals? Okay, your answers are in. Let's go on to the next one. So what about things that are just nonmetals? If you have 2 nonmetals, where would you drag the icon to? Most all of y'all are right. You drug it to covalent, because a covalent molecule is one in which the electrons are shared, and 2 is one in which the electrons are shared, and that typically occurs between 2 nonmetals. The first one y'all were also right about. That first one is ionic, because ionic things are a combination of a metal and a nonmetal. And then the last one, what does it take for a metallic bond? And a metallic bond is, of course, 2 metals. So you can drag the icon and be totally right again, but you can rest assured that metallic ones are the easiest ones to see. And then finally, which one has the typically greatest amount of energy necessary to break that bond? Which one do you think is true? An ionic, a covalent, or a metallic? Which one do you think typically has the greatest energy necessary to break that bond? looking at y'all's answers, you're kind of all over the place, and that's great. In truth, there are some ionic bonds that are stronger than some covalent bonds, and there are some covalent bonds that are stronger than ionic. Some metals melt at a very low temperature, and some metals melt at a very high temperature. But by and large, if we had to guess who probably has the most amount of energy it takes to break that bond, usually that is covalent. So a little bit about what metallic bonds are. Y'all have learned about ionic and covalent before in a lot of different classes. So we'll come back to those in a little bit. But for right now, metallic bonds are the ones y'all tend to struggle with the most. So basically, metallic bonds are a bunch of atoms who are looking to give away electrons. That's why we call them cations when they give them away. But all they're doing is hanging out with other metal atoms who all want to give away electrons. So no one's really taking electrons. So you get a positive nucleus, and then you have a whole bunch of what we call delocalized electrons, or electrons that nobody's really trying to keep track of. It's metal ions and a whole big soup of electrons. Typically, they form a crystalline structure at room temperature. So think of any metal, not mercury, of course, but any metal will typically be a solid at room temperature, and they have that crystalline structure, which means a regular repeating structure. And of course, we get all kinds of different melting points. So gallium would melt if you held it in your hand, like an M&M, whereas other metals you would have to get to be thousands of degrees before they would ever melt. And then it comes down to conduction. So metals, we know, are good conductors of electricity, and they do that either as a solid or a liquid. And that is because all those electrons in that solid or liquid state are still delocalized and they're able to move around. So here's that sea of electrons, and you'll notice that each one of those positive things is one of those nuclei of the metal, and then you have that sea of electrons floating around them. We call a mixture of different metals an alloy. So you can see in the upper left-hand corner, that's just all one type of metal. And then you've got two situations. A substitutional alloy is where you've taken out some of the red atoms and you've replaced them with a different, kind of similarly sized metal. You probably know of lots of alloys. So there's 14 karat gold, where it's not all gold. That gold is actually mixed with something else. Brass is a mixture of copper and tin. Notice that the interstitial alloy is different because it's got tiny little atoms that fit in between the red atoms. And those interstitial alloys don't involve removing any of the red metal atoms. It just involves packing those smaller ones in there. So on Pear Deck, if you would go ahead and circle the one that you think is the metal. So which one do you think is the metal? You guys are pretty right. That's right. So this upper one in this right-hand corner has those electrons kind of floating around it with positive centers. Which diagram or diagrams are ionic? Again, on Pear Deck, if you would circle the one or ones that you think are ionic. Again, you guys are crushing it, so that's great. If you notice the ionics are made up of a positive and negative thing. And the two on the left over here, this one and this one, are definitely ionic. What's the difference between the two? Well, the top one, it's got similarly sized ions. And remember, we talked about radius in terms of periodic trends. Well, if you're talking about radius, then you're talking about the size of ions. So we also have to keep thinking about those periodic trends and Coulomb's law, even when we're talking about bonds. Out of all these molecules up here, which ones look covalent? And while it's hard to decipher, go ahead and take a stab, draw anywhere on the slide, and go ahead and circle the one that you think is covalent. Again, you guys are really good today, so you are identifying the correct one. Notice over here on the right, that's a molecule. That's a macromolecule, whatever it is. But we know it's covalent because it's not made up of positive and negative charges attracting each other like the ionic and the metal are. So this time I just want you to look at the two on the left. Circle the one that you think is KCl. You may need to look at your periodic table and make sure you look at the periodic table and try to figure out which one is KCl. All right, y'all are about evenly split, so let me bring in the periodic table real quick. K is in the fourth row, but when it loses electrons, it actually has valence electrons in the third energy level. So when potassium loses electrons to become a positive charge, it looks like argon. So it has 3 layers of electrons, 3 occupied energy levels. Cl, on the other hand, Cl will gain electrons, and it too will look like argon. So at the end of the day, the potassium and the chloride are really going to be similarly sized. Now, one might be slightly smaller than the other, but in general, they're going to be the same size. So if we look at the molecules here, I would say this top one is a better representation of KCl because K is a +1 charge and Cl is a -1 charge, and also they're relatively the same size. So which one would be NaCl? Well, before you answer, look at the periodic table again. Think about Na, and when it loses an electron, who it looks like. And Cl, when it gains an electron, what does it look like? Go ahead and circle the one that you think is right. Okay, not too bad. So what you're seeing is that the bottom one, because really it's the only one left, but the bottom one is better for NaCl because Na will actually only have 2 occupied energy levels when it becomes an ion, and Cl will have 3 layers of electrons. So Cl should be bigger than the Na ion. So looking at all these and remembering what we talked about earlier, what is an interstitial alloy? So you can take your icon, the thumbs up icon, and go ahead and drag it on top of the one that you think is the interstitial alloy. All right, I like this. So yes, the top left one, this one right here, is the interstitial alloy. The one that's not substituted, the one where we fit the smaller atoms in amongst the bigger atoms. Which one do you think is the substitutional alloy? So the one that looks the most substitutional to me would be letter C, and you can see this top right one right here, where some of the circles have been taken out and shaded circles being put in. That's substitutional. The one at the lower right can't possibly be the answer. That's an ionic solid. So this is where you get to vote. So I want you to drag your icon either under the ionic or under the covalent. Which one of those conducts electricity as a solution or when it's molten? And molten is a fancy word for saying when it's heated up and it becomes a liquid, not in water, but when you get something so hot that it actually melts. So you go ahead and vote. All right, let's see what column it belongs under. So a lot of y'all got that right, but ionic things are good conductors of electricity, either in solution or when molten. It does not happen when it's solid, because when it's solid, the electrons aren't free to move around. Those ions are locked into a 3D structure, but either dissolved in a solution or when they're molten, when they're liquid, those ions are able to move around. So let's try this one. Relatively low melting points. Does that belong under ionic or does that belong under covalent? Getting a lot of answers, okay. And the answer is covalent. You're right. Covalent things typically have relatively low melting points. That's because in covalent stuff, we're breaking intermolecular forces. We're breaking the bonds between 2 water molecules. Not inside of the water molecule, but between 2 molecules. And that's a later unit, nothing to worry about now. but covalent tends to have relatively low melting point. Okay, let's try this one. They can exist in any state of matter. Like, don't be ridiculous and say in space, or like, oh, if I get my oven to several thousand degrees. Just normal things. It can be a liquid, gas, or a solid. Okay, I'm getting lots of answers. Let's see how you did. The covalent can exist in any state of matter. You get some that are very, very light and they're gases. So think of oxygen gas. Then you get some that are liquids, and you can think of things like bromine or water that are actually a liquid at room temperature, normal conditions. And then you get some that are so heavy that even though they're covalent, they have so many intermolecular forces, it becomes a solid. And so a good example of that is something like plexiglass or something like asphalt. So let's look at exist in a crystal lattice. Do you think that belongs under ionic or covalent? Your choice. All right, getting lots of answers. Let's see. That's right. Crystal lattice is what you see pictured here. That crystal lattice is a regular repeating structure. So the NaCl, this is salt. The Na would be the tiny purple thing, and the Cl ion would be the big green thing. So ionic things exist in a crystal lattice. Covalent things do not, because they don't have that regular repeating structure. They're just random molecules existing around each other. Which ones, covalent or ionic? They don't conduct electricity as a solid. So go ahead and drag the icon and vote. Which one does it go under? Is it ionic or covalent? Things that don't conduct electricity as a solid. And you're actually, whatever you said, you were exactly right. Ionic things don't conduct electricity as a solid because, remember, those charges aren't mobile. They can't slide past each other. And covalent things also don't conduct electricity very well. Rubber is a covalent compound, and because of those covalent bonds, it really doesn't have loose electrons like a metal would have, or loose ions like a liquid ionic substance would have. So let's try this one. What happens between atoms that have similar electronegativity? Is that an ionic bond or is that a covalent bond? So you'd look up numbers of electronegativity, and if they're similar, not exactly the same, but if they're pretty close, which one would it be, ionic or covalent? Drag the icon to the one you think it is. Okay, most of all of y'all are on the right kind of track, and that answer is covalent. Covalent things occur between things that have similar electronegativity, because ionic things happen when one thing is really electronegative, it's really pulling hard on the electrons, and the other thing is not very electronegative at all. So imagine somebody that you hang out with, you're much stronger than them, and you're supposed to share something with them. If you're much stronger than them and you can just rip it away from them, then I wouldn't call that a sharing anymore. You get that thing more often and they don't ever get it. And since you get it, you get that thing all the time and they just don't get it. That's exactly what an ionic bond is. When one thing is very electronegative and gets the electron, and the other thing is not so much and loses the electron. So here's a question that you might see on the AP exam. Lattice energy. Now, what is lattice energy? Lattice energy is just the energy released as things form. So whenever you make a bond, energy is released. Whenever you break a bond apart, energy is absorbed. So when you form MgO, when you make that ionic bond, it releases energy. So the calculation for that is actually going to be very, very similar to the calculation for this is going to look just like Coulomb's law. Magnesium has a +2 charge and oxygen has a -2 charge, whereas sodium has a +1 charge and fluorine a -1 charge. And if you notice, the calculation for lattice energy looks a lot like Coulomb's law, Q1, Q2 over R. And again, you only want to worry about the R factor or distance when the Q1 and Q2 are the same. In this particular instance, we've got +2 and -2 and +1 and -1. So let's see how we would answer that question. So based on what we just talked about with lattice energy, being somewhat like Coulomb's law, you can go ahead and choose an option. Do you think it's A, B, C, or D? Go ahead on Pear Deck and choose that now. So we know that it's not C because we don't care about smaller or larger or anything like that. And in truth, the F ion is actually smaller than the oxygen ion. And that's because oxygen has one less proton than fluoride ion, and fluoride ion has more protons pulling on those electrons. So C is out, D is just mumbo jumbo gibberish, and so it comes down to be between A and B. A doesn't make any sense because Mg is more positively charged than sodium. And so the answer really comes out, the one that's best is B. O with a -2 charge is more negatively charged than fluoride. So if we look at it again, we'll think about it. If we look at the equation over here, Q1 times Q2, all you have to do is do the math. +2 and -2 is -4, +1, -1, -1. So who's got a greater lattice energy, 4 or 1? You don't worry about the negative, you just worry about the number. And it turns out that magnesium with a +2 and oxygen with a -2, it just has a greater lattice energy, which means it's got a stronger ionic bond. Here's an FRQ that you may see out there in the world. In 1 year, they came up with this kind of general question. The first parts were all about all other kinds of subjects, and then it came down to this was the very final part of the question. A student hypothesizes that the thing formed is ionic. Propose an experimental test. So what is something that the student could do to test whether or not it's ionic? Well, we've talked about the difference between ionic and covalent. Think about that and go ahead and write your response. So provide an experimental test. What would you do? Okay, so those are some decent answers. Propose an experimental test. So the student could dissolve it in water and test to see if it conducts electricity. Or it could melt it and see if it conducts electricity. Remember, solid ionic things don't conduct electricity. Or they could also measure its melting point. And in general, ionic things tend to have high melting points. And covalent things tend to have low melting points. Either one of those would be an acceptable answer. Now, explain how the results of the test would support the hypothesis. This is where you would have to go a little bit farther. So propose an experimental test is kind of like saying make a claim. So we could say, all right, I would melt it and test for conductivity. That would be the first part of the answer. And then the second part of the answer would be explain how the results of the test would support the hypothesis that it is ionic. So make sure that when you answer these questions that you're going ahead and answering both parts. So you can't just say melt it, or you can't just say dissolve it in water and see if it conducts electricity. You have to go a little bit farther and say if it does conduct electricity, then it's ionic. Or if it's got a high melting point, it's ionic. So you get 1 point just for the test, and you'd get another point for supporting the hypothesis. The best way to make sure you don't earn points on an FRQ is not to answer the entire question. So make sure you're doing all the parts. Come up with a test and explain what the results of that test would look like. Right? Well, hopefully this gave you a little bit to know about bonding. Hopefully this was a little bit of a review for y'all about bonding and the different types of bonding that can be. Next week, we'll continue and get into Lewis structures, drawing Lewis structures and what those molecules look like when they share electrons. See ya.